Hello, 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 hello. Hello, hello, hello. Okay, hello. So before starting today's class, let me discuss the things that we have done in the last class. So, so in the last class, we basically discussed about different types of uh, different types of systems and different types of processes that is used in the classical thermodynamics. So, so in the previous class, we started with the systems. We started with the three types of system we know. So there is one called open system. Open system is where the particles, the boundary of the system is made in such a way that the system can exchange particle with the surroundings. Okay, system exchange particles. Second is the closed system. Closed system means uh, system boundary doesn't system boundary doesn't allow exchange of particles. Third is the insulated system. The insulated system is a system where um, there is no exchange of heat or energy. And fourth one is diathermic system. Okay, where system can exchange heat with surroundings. Okay, so there are primarily these four types of systems are there, and also we discussed about two types of parameters that we generally deal in our classical thermodynamics. One is known as intensive parameters. And second one is the extensive parameters. The intensive parameters are basically the parameters that directly depends on the mass of the system. Okay, depends on mass. Sorry, it does not depend on the mass of the system. Does not depend on mass. Okay, so does not depend on the mass of the system. So that means that like pressure, temperature. So let's suppose in a gas chamber, if you decrease its mass or something like that, but by doing so, its pressure or temperature doesn't change at all. Okay, so in that way, this pressure, temperature, all these parameters basically comes under the intensive parameter section. Okay, so pressure, P, temperature. So all these things are intensive. Extensive parameters are the parameters which depends upon the mass of the system. So like volume. So if you like reduce like reduce some of the mass from this gas chamber, some of the mass of the gas. By doing that, you basically reduce the volume of the gas. Okay. So in that way, the volume is basically extensive parameter. Okay. Like volume. Then you also talked about different types of equilibrium. So there are three types of equilibrium. So if a system basically obeys all these three types of equilibrium, then you can say the system is in thermodynamic equilibrium. Okay. So thermodynamic equilibrium means three types of equilibrium. One is the thermal, that is if temperature is that means if temperature is equal of both those the systems and the surroundings. So T should equal. Next one is the mechanical equilibrium, that is basically related to the pressure. And third one is the chemical equilibrium. So chemical equilibrium means like if there is no exchange of particle of between the system and the surroundings, then you can say the system is in chemical equilibrium with the surroundings. Okay, so basically if the system follows all these three types of equilibrium, then we can say that the system is in thermodynamic equilibrium. Then we have also talked about two types of to also different other types of processes that are also very important in thermodynamics. Those two processes are basically irreversible and reversible processes. Okay, so irreversible processes, from the definition itself you can basically know, so that you can basically, so if the system basically uh, moves from one state to another state through a irreversible process, in that case you can basically does not turn that system back onto the initial system, initial state. Okay, so you cannot switch back to the initial state from the final state. Okay, so this is basically a definition of the irreversible process. Okay, so if basically during the process, if there is some dissipative force that is involved in the process, in that case the process is known as irreversible process. The reversible process, like if there are no such kind of dissipative forces are present, in that case the process is basically known as the reversible process. So you can basically switch back from final state to initial state also. Okay, so here dissipative forces exist, there is no dissipative force. Next thing that we have also discussed, also a very important process, that is known as the quasi-static process. Okay, so this is the important of this quasi-static process is that in thermodynamics, this is basically a hypothetical concept where basically we uh, change one of the variable or parameters of a thermodynamical system in a very small amount, you can say infinitesimal amount, such that uh, during before the process and after the process the system basically retains at its thermodynamic equilibrium. Okay, so it's like if you change any if you change any kind of thermodynamic parameter, let's suppose x, a very small amount, delta x, infinitesimal amount. Okay, and if the process is quasi-static, so that means from x to x plus delta x, x to x plus delta x, the system will still retain at its thermodynamic equilibrium. So that is basically the significance of the quasi-static process. Okay. After the quasi-static process, there are also there are other kinds of processes that is important in thermodynamics, that are known as, first is the isothermal process. So isothermal is basically, from the name you can guess it. So temperature basically remain constant in this during isothermal process. So temperature will remain constant. The next is the adiabatic process. During the adiabatic process, there will be no heat exchange between the system and the surroundings. Okay, so delta Q would be zero, no heat exchange. Third one is the isochoric process. Isochoric means uh, the volume will remain constant. Okay, the change in volume delta V is equal to zero. And the fourth one is isobaric. So here delta P is equal to zero. Okay, so these are basically four types of processes, very important thermodynamic processes. Okay, so for each types of process you have to basically know what are the things that are kept constant. Okay, right. So so in order to solve problems, you have to know, in the problems actually they mention what types of processes that we are basically dealing with. So by that name you have to figure out which are the thermodynamic variable that are constant associated with the process. Okay. Next, we have discussed about the uh, first law of thermodynamics. Okay, so from the zeroth law of thermodynamics, you already get an idea, get the concept of temperature, right? That we have discussed in the last class. Now, from this first law of thermodynamics, we get a relationship between the how the change, how if you do any kind of work done into any kind of thermodynamic system, in that case, how that work done is related with the change in heat and also the change in internal energy of the system, how basically that work done is related with those two quantities. So that relation is given by this first law of thermodynamics. Okay. So the first law of thermodynamics states that the change in internal energy of the system, delta du, is equal to dq, that is the exchange of heat, amount of exchange of heat minus dw. Okay. So this is for the case of an closed system. So we assume that the system doesn't exchange any particles with the surroundings. And if you don't consider that, if you consider the system as an open system, so there would be also third term that would be mu dn. Okay. Now for our case, we only consider it's a closed system, like for uh, our case. Okay, so in that case, du will become dq minus dw. Okay. Now we also have calculated, like for each of these four processes, we have calculated what is the work done. Okay, what will be the expression of this work done. Okay, so like for isothermal process, hmm, for isothermal process, uh, we have find out that the work done is basically W equal to RT ln V2 by V1. Okay. For adiabatic process, we have discussed about the polyotropic process where for the adiabatic case, we know the system for an ideal gas basically obeys PV to the power gamma equal to K, this kind of relation. So in that case, you have calculated also the work done expression looks like this: W equal to NR. Here N is the mole, okay, NR. So let me tell it mu, okay, mu is the mole, mu R by N minus 1 or gamma minus 1, okay, into the initial minus the final. Okay. Similarly, for isochoric process also you have calculated the work done, that is W equal to P V2 my V final minus V initial. Okay. So these are different expression of the work done for associated with different processes. Okay. And from this from this work done expression, you can also calculate other thing, how what is the heat exchange, what is the internal energy change. Okay. Now there is also another way you can calculate this internal energy, change in internal energy of the system. That is, if you know the specific heat of the system with constant at a constant volume, that is we denote as CV. We know the CV. So from that also you can also calculate what is the change in internal energy. So we know that CV is basically dq by dt at constant volume, right? Now if you so you already know dq is already equal to du plus dw, right? And dw you can write it as pdv. Now if you take a volume as constant, so that this term will become 0. So now you can write this as du by dt at constant volume. So from this also you can write du equal to cv dt. Okay. Since from using this relation also you can calculate what is the change in internal energy. Okay, if you know the du. So these are the some of the important things, important concepts and important formulas that we have discussed in the last class, and this is also very important in terms of solving problems. Also have to remember, like also like some way, at least you have to have an idea how these formulas and all is coming. So today's class will be starting from uh, this yeah. So first we'll be discuss about more about this polyotropic processes. Okay, where, or you can say this adiabatic processes. Okay, so where basically for an ideal gas, it obeys the PV relation of this for the case of an ideal gas. During an adiabatic processes, it relays this kind of relation PV to the power gamma equal to constant. We already discussed about this. And this relation you can also write in different way also. Okay, in terms of other thermodynamic variable also, like you use this relation PV equal to RT you can write P in terms of temperature and volume. You can substitute this here. From after doing that, you can write this equation in terms of T and V also. So the relation would become T V to the power gamma minus 1 equal to constant. Similarly, you can write in terms of P and P also. In that case, the relation will become T gamma T1 minus gamma equal to constant. Okay. Depending upon the problem, you might have to use either of this, any of this relation. Okay. uh, Whether it's the relation between pressure volume or temperature pressure. Okay. Now, so what is the difference? So if you see the PV diagram of both this isothermal process and adiabatic process, from a qualitative perspective, it might look similar, but there is a difference. Okay, there is a difference between the slope actually. Okay, so for a isothermal process, the relation is for an ideal gas. The relation is simply PV equal to RT. Yeah. Now, so the so so from here, if you calculate uh, the slope of the isotherm, like slope of the curve due for an isothermal process, that would take a form dp by dv equal to minus p by v. Okay, if you take v to the right hand side and if you do the derivative and all, you will be getting dp by dv equal to minus p by v. Now this would be the slope of that isotherm. So isotherm means this is the curve for a isothermal process looks like. And if you calculate the slope of this curve, okay, the slope of this curve, okay, that slope basically dp by dv equal to minus p by v. Now if you take an adiabatic process, in that case the slope you have to calculate the slope from this relation. Okay, so if you calculate from this relation, the dp by dv will become dp by dv will become minus gamma p by v. So if you compare it with the isothermal slope of the isotherm, you can see there is extra term gamma. Okay, and this gamma is basically greater than 1. Okay, for a for a normal process it is equal to 1, and for a diabetic process this is gamma is greater than 1. So that means the slope for this isotherm, slope for this adiabatic process is steeper compared to isotherm. Okay, so if this is the PV diagram of isotherm. Okay, the for a adiabatic process, this 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 diagram will become a bit steeper. Okay, so this is isotherm, this is for adiabatic. Okay, so this is in general a difference between an isothermal process and adiabatic process. So, the slope is a bit steeper in the case of adiabatic process. Okay, because of that. Okay, so next, the adiabatic, one of the important, the example of the adiabatic process is our temperature. Okay, like in our atmosphere, basically the hot gas goes into the top, like hot gas in our atmosphere. The gas which are close to the ground basically become hotter, and hotter gas we know uh, they are like they become lighter, basically hotter gas. So it goes to the upper part of the atmosphere, then it can becomes cooler, and it basically, so during that process, so the hot air when become cooler, so that entire process is basically adiabatic process. Okay, and using this relation T to the power gamma T 1 minus gamma equal to constant, if you do all the derivative and all, after doing all this thing, you can basically calculate what is the change in temperature. So So since the hot air goes to the upper part and become cooler, so there would be a gradient of the temperature exist into the into our atmosphere, right? If you want to calculate that gradient, you can use this formula for adiabatic processes, and using this formula, this temperature gradient takes this kind of form: dT by dH equal to minus gamma minus 1 by gamma into Gm by R. Okay, yeah. So this is a very useful relation. So this relation, what it tells is that with height. So if as you gradually move towards uh, uh, like small altitude to high altitude, in that case, how the temperature is changing. Okay, so that relation is basically given by this equation. Okay, so is this, as you can see, this depends on many things. It depends on what is the gamma. That gamma is, we see, entirely depends upon the composition of the air, right? And also it depends upon the m. M is, I guess, is the molecular mass. Yeah, m is the molecular mass of the air. Okay, so these are the two important parameters. Okay, depending upon that, you can calculate this lab. This is known as the lab state, adiabatic lab state in our atmosphere. Okay, and this negative signs, this minus v sign, basically indicates that how the temperature drops with the height or age. Okay, okay. So next, okay. Mm, okay, so next we will discuss another important concept that is known as the cyclic process. Okay, cyclic process. This is also a very important concept that we'll deal in classical thermodynamics. Okay, so what is a cyclic process? Cyclic process is basically a process where uh, the system, uh, the system initial state and the final state, both the states are if equal, then this process is known as a cyclic process. Okay, so in this process, the system's initial and final state is same. Okay, so that means if you observed it in a PV diagram, it looks like this. Okay, so the system starts from let's suppose from an initial state I from here. Okay, or yeah, so let's take I from here. So from initial state to a final state F. Sorry, not like this. Let name it like 1 and 2. Okay, let's start from point 1. So the system starts from point 1, it moves to another state 2, and from that state it again comes back to the same state 1. Okay, so as you can see, the system basically started from 1, and at the end it moves back to 1. So it's a complete closed circle, closed cycle. So it known as a cyclic process. Okay, so this path can be any kind of path. It can take, this kind of path and goes back from this path. Any kind of path it can take. It can this path, whatever the path is. It's path it's like doesn't depend. Okay, all of these processes are basically starts from the point 1. It's inside the point 1, so it's qualify as a cyclic process. Okay, and one of the important properties that is very important. Okay, That is very important to remember actually. So delta U is 0, okay, during this cyclic process the change in internal energy, that would be equal to 0. So that means whenever in the problem it mentioned that it's a cyclic process, so in that problem we have to consider the delta U equal to 0. So maybe in that problem you have to use this first law of thermodynamics, okay, this law maybe, okay, d equal to dq minus dw. So whenever you see the system is cyclic, so that means you can safely make this d equal to 0. So that means dq will become equal to dw. So for that particular problem, the change in the work done is basically the change in heat, okay, the exchange in heat, okay. So this is one important thing to remember for the case of a cyclic process that we'll see. Let's take an example for that, okay. So let's take this example. So let's take the PV diagram. Okay, so system, let's say, starts from a point A. So it's take this kind of path, okay. Started from A to B like this. So this is a, let's take this A to B is an isothermal process. Now from A to B it moves to C. Then from C, then it again goes back to A. So let's take the temperature of a T, B also T. So since it's an isothermal process, so and Cs T by 2, okay. So this is isothermal. This process is isobaric. This is isobaric, and this process is isochoric, right? So as you can see, since this is a class cyclic process, so we can take, so du equal to 0, right? D equal to 0. So dq equal to dw, right? So if we want to calculate what is the work done into the system, simply have to calculate what is the heat exchange. So heat exchange you can easily calculate, right? So for delta, for dq AB, we know for an isothermal process the work done is simply this relation, right? So let's take consider this volume as 2V and this volume as V, okay, and this pressure is as P, okay. Now for QAB, so during this process the work done would be nRT into ln 2V by V, so nR ln 2. The during PC the change in heat would be, so it becomes T to T by 2, so nR T by 2 minus T, so it would be minus nR T by 2, right? So it would be the heat. So in this case the delta Q is plus, so delta Q plus means the heat is basically goes into the system, and minus means this heat is basically coming out from the system, okay. This minus sign here, sorry, this minus sign here basically indicates that the heat goes out, okay. And during delta Q, Ca, Cp, sorry, Cp, Cp, this delta Ca, so T by 2 to T, right? So NCA Cv, so this is T minus T by 2. So NCV T by 2, okay. So this is here, uh, okay. So during AB and CA, the heat is coming in, goes into the system, and during BC, heat is going out to the system. So the delta W, that means would be delta W would be delta Q, right? So delta Q is nothing but this one. So here delta Q, delta W equal to Q1 minus Q2. Okay. So here Q1 is the heat that is goes into the system. So that in our ln2 minus plus sorry ncv t by 2, right? And his that is going out, that is given by ncp t by 2, right? That we have already calculated. So that is basically the work done. Now from here you can also calculate the efficiency of the cycle also. This is also important point. So for any cyclic process you can calculate its efficiency. That we'll also discuss in case of a Carnot engine also. Like for this process also you can calculate. So efficiency, general formula of efficiency of any cycle, okay, is given by eta equal to work done by heat input. Okay. So so work done is nothing but Q1 minus Q2 by Q1, or 1 by Q2 by Q1. That means 1 minus Cp for this cycle. For this problem it would be Cp by Cv minus R by 2. Okay, this is a general formula for any to calculate efficiency of any cyclic process. Okay, and for this process, if you since we got, you can calculate the expression of heat input and heat output, and from that if you substitute it here for this process you'll be getting this expression as its efficiency. Okay, next we'll discuss about the heat engine. Okay, so this is a very important concept in thermodynamics. Okay, heat engine. So what is a heat engine? So heat engine is basically uh, convert heat into the mechanical work. Okay, so how it does that? So we know that heat basically spontaneously flow from a from a hot reservoir. Okay, hot reservoir to a cold reservoir. Okay, so here temperature is, let's suppose T1, it says temperature is T2. So T1 is greater than T2. Okay. Now, during this flow, what a heat engine does is that it converts some of the heat into some mechanical work. Okay. So W is, so if it pulls the heat Q1 amount of heat from the hot reservoir, now uh, it converts some of the heat to some work, and and the remaining heat, let's suppose that is as Q2, will move to the cold reservoir. Okay, so in that case the work done that is done by this reservoir, that is nothing but the heat that is absorbed. Okay, so that amount of heat would be Q1 minus Q2, right? That is simply the work done, right? So this is the work, this is like the principle of any kind of heat engine. Okay, so it basically the heat that is flows from the hot reservoir to cold reservoir. The heat engine basically extracts some of the heat into mechanical work. Okay, and for a ideal heat engine, the efficiency is basically given by eta is given by. So for any general for the general formula is like this: efficiency of the heat engine eta equal to, as we have discussed what is the definition. So this also if you see the PV diagram of this heat engine, it also follows a cyclic kind of diagram. So for this cyclic process, the expression of heat engine would be same. So it would be uh, delta W by the heat input, okay, Q1, right? So eta would be Q1 minus Q2 by Q1, or 1 minus Q2 by Q1. This is the general expression of the efficiency of a heat engine, okay. So now, if you consider an ideal heat engine, it's basically the how it looks like. So this PV diagram looks like this. Okay, let me draw. So the PV diagram of an ideal heat engine looks like this. Okay, so this is the whole process. So this, as you can see, this is a completely cyclic process. Okay, so here, how what are the four? Then what is this four curves signifies here? Okay, now from the slope of the curve, you can easily identify what kind of processes it is basically uh, 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 showing. Okay, so now you can see this AB process. So this AB, there are AB, BC, CD, and DA. Okay, now as you can see the BC and AD process, for these two processes, you can see the curves are a bit steeper. Okay, so that means these BC and ED processes are basically adiabatic processes. Okay, BC and AD are adiabatic process. Okay, we have discussed earlier also, right? The for the adiabatic processes, the curves are steeper. The PV curves. Okay, now so that means the other two, the AB and DC, these are like will be the isothermal process, right? Automatically. Okay. Now, so that means during this AD and BC, during these two process, since these are adiabatic process, so during this process there will be only change in temperature. Okay, there will be uh, so if this process is in T2 temperature, this process will be is in T1 temperature, right? So there will be no heat exchange, and during these two processes, this AB and DC process. So during these processes, these are isothermal process. So here temperature will remain same. Let's take this AB process is in temperature T1 and CD process at constant temperature T2. But this processes during this process it can exchange heat. Okay, so during this process it can uh, there is some input of heat Q1, and during CD process there is some uh, the heat that is basically goes out from the engine, that is Q2. Okay, now this Q1 Q2 you can easily calculate for an ideal gas. For an ideal process you can easily calculate, not ideal process, for a general process we'll consider after that how, what is the condition for an ideal process. Okay, for a general process, isothermal process, the heat is basically given by Q equal to nr T1 ln Vb by Va. Okay, so Vb is the volume at D and Va is the volume at A, and Q2 is nr T2. Remember here the heat is basically going out. Okay, ln Vc by Vd. Okay, now if you just substitute here into the expression of eta, it would become 1 by 1 minus. So if you substitute the expression of Q1 Q2, it will now become T2 by T1 ln Vc by Vd ln Vb by Va. Now, for the case of an ideal gas or an ideal process, we know that the adiabatic relation, this adiabatic, since these two processes are adiabatic process, okay. the temperatures, basically the temperatures are related by the adiabatic process T1, T2. We already knew that. So we can use that formula for an ideal process for an ideal gas. This T1, T2 temperature is related by this formula, right? T1 VB gamma minus 1 and T2 VC gamma minus 1, right? This T1, T2 temperature is related by these two isoadiabatic processes. Okay. Now from here we can write, and also this is one way, this VB BC. So this relation. Also in the other way also it is related, T2 VD gamma minus 1 and T1 VA gamma minus 1. So one is coming from this adiabatic process, one relation is coming from this adiabatic process. Okay. So now you can take a ratio of these two relation, which basically gives you VB by VA gamma minus 1 equal to VC by VD gamma minus 1. Okay. Now, so that means, so that means VB by VA equal to VC by VD. So now if you substitute this thing here, so that basically cancel out this ln VC by VD and ln VB by VA, right? So which gives the relation eta equal to 1 minus T2 by T1, right? Yeah, this is the efficiency or ideal case. Okay, or you can say the maximum efficiency. Okay, for an heat engine or Carnot engine. Okay, so this is a general expression of an heat engine, and this is for the ideal case. Okay, or the maximum efficiency of an heat engine. Okay, so so that means in the ideal case it doesn't depends upon the working substance or anything like the internal behavior, internal substances of the engines. It's entirely depends upon only the temperature. Okay. So after the heat engine, there is another type of engine that is known as the refrigerator. So so the refrigerator, the concept a bit opposite here. So here instead of heat going so in case of heat engine, the heat is flowing spontaneously, from uh, hot reservoir to cold reservoir. Now here what we do, we are basically forcing the heat to move from a cold reservoir to a hot reservoir. Okay. Now, so this is not a spontaneous movement. Okay. So to make that thing possible, you have to do some external work onto that engine. Okay. This engine is basically known as the refrigerator. Now, in this refrigerator, you have to put some external work. Let's denote that work as W. So you take some heat from this. So because of that work, you basically take the heat from cold reservoir and moves to the hot reservoir. Okay. So Q2 is taken out and Q1 is going in. Okay. Now, since we are doing some work onto the system, so there is no concept of efficiency there here actually. So instead of defining efficiency, we are defining a separate quantity that is known as the coefficient of performance, or in short known as COP. COP is basically known as heat extracted from cold reservoir divided by work done on the refrigerator. Okay. So COP, the expression of COP is known as the heat extracted is Q2 by the work done W. Okay, so Q2 is W is Q1 minus Q2. Okay, COP, coefficient of performance. Okay. Okay, so similar way for if you consider an ideal case, the COP can take a expression like this T2 by T1 minus T2. Okay. So T1 is the temperature here at hot reservoir, T2 is the temperature here at cold reservoir. Okay, for ideal case. Okay, so this COP also some denoted by omega sign. Okay, these are the two important types of engines. Okay, one is the heat engine and next is the refrigerator. So what are the processes that are involved during the operation of both of this heat engine and refrigerator is important. And also have to remember like what is the expression of the work done, what is the expression of the heat input, okay, what is the expression of the eta or this efficiency, and what is the expression of this coefficient of performance for the case of refrigerator. Okay, these things you have to remember. Now next, so we have already discussed the first law of zeroth law of thermodynamics and the first law of thermodynamics. Now next will be discuss the second law of thermodynamics. Okay, so for the second law of thermodynamics, there are basically two statements are there. One is the Clausius statement, which basically states that no process is possible uh, that is to transfer heat from a colder to hotter process. Okay, so from so no so if there is let's suppose a cold body and a hot body. So we know that there is no spontaneous process, right, that can flow heat from cold body to hot body. Okay, so no spontaneous process moves heat from cold to hot body. Okay, like we see in the case of refrigerator, you have to use the engine and you have to put some work onto the refrigerator in order to pull out some heat from cold to move to hot, right? Similarly, so this is first statement for Clausius statement for second law of thermodynamics. Now, the next statement is given by the two scientists basically. So they have combined the statement of these two scientists, okay, and they make it as Kelvin-Planck statement, okay. This statement gives this that no process is possible whose yeah. So here it's like no process is possible to like which results into to absorb heat from a reservoir and convert it completely to work. Okay, so no process possible to convert heat from hot body completely to work. Okay, so it's like from the heat engine. So it comes from the heat engine concept. Okay, so heat engine basically takes some heat from hot and it moves to cold, right? Like when the heat flows from hot to cold, so this heat engine basically extracts some work from it. Okay, now according to the Kelvin Planck statement is that uh, it, it is not like that the Q1, the heat that is basically pulling out from this hot reservoir, it is entirely converted into the work. Okay, so Q2 basically becomes zero, right? So this kind of thing is not possible. Okay, so this thing is not possible. You cannot simply put the entire heat into work done. Okay, yeah. So if you do that, in that case, the eta for your case, eta we know 1 minus q2 by q1. Okay. If you do that, then your eta will become simply 1. So efficiency will become 1. The engine will be 100% efficient. So that is not possible. No engine in real life can be 100% efficient, right? It should lose some of its, during some work, it will lose some of its energy as a heat, right? These are the basically two statements of the second law from the second law of thermodynamics. Okay. Now, okay. So now, now using these two laws, uh, these two laws, Clausius and Kelvin-Planck laws, there are also two statements. Okay. So two theorems you can say. One is known as the Carnot theorem. Okay. So the Carnot theorem. So what this Carnot theorem says is that the working between the same two heat reservoir, no engine can be more efficient than a Carnot engine. Okay. So Carnot engine is the engine where you consider the ideal cases. Okay, so where the eta is basically 1 minus T2 by T1. Okay. So this means that, so if your heat engine is working between temperature T2 and T1 and T2, then the maximum value of eta it can take, eta equal to 1 minus T2 by T1. Okay, this is the maximum efficiency that engine can attain. Okay, this is known as Carnot's theorem. Next is the Clausius theorem. So Clausius theorem is basically Uh, so Clausius theorem states that for an irreversible engine, so if there are two coefficient, two efficiency, let's suppose there are two types of engine. One is the Carnot engine, where the engine is reversible, okay, and there is another engine that is the ordinary engine. Let's suppose that is not reversible, irreversible engine, okay, that is the real life irreversible, okay, the process involved with the ordinary engine is irreversible. And let's suppose for Carnot engine, the efficiency is given by eta E, and for the ordinary engine, the efficiency is given by eta C, okay. Now in that case, sorry, let's take this one as eta C and this one as eta E, okay. For so eta E should be, for the case of ordinary engine, eta E should be always less than eta C, okay. So that means if the cycle, so that means if the cycle is reversible, for that case, if in the engine the cycle is irreversible, sorry, irreversible, so in that case, the efficiency should be always smaller than the efficiency of the reversible engine. Okay, so this is the statement of the Clausius theorem. Okay, now we'll discuss about the Clausius relation of the for the irreversible cycle. Okay, so there is a so so this is also very important concept. Okay, so Clausius relation for irreversible cycle. Okay, so let's take there is from one state, consider from a state 1 to state 2. So there are, let's suppose two types of processes happening. One is reversible, one is irreversible. Reversible process looks like this, very smooth from here to here, and let's suppose there is another process which is irreversible. It takes some kind of this kind of form. Okay, okay, so one is reversible and one is irreversible. So eta E is the irreversible one, let's suppose. So in that case, uh, let's denote this efficiency as 1 by Q2 irreversible by 1 by Q1 irreversible. Q2 is the basically heat that is given that is moving to the cold body, and Q1 that is heat taken out from the hot body. Okay, and for the reversible one, the eta C is basically 1 minus Q2 by Q1. Okay, so from the Clausius theory we know that eta E should be always smaller than eta C, so that means 1 minus Q2 IRR by 1 by Q1 IRR less than 1 minus Q2 by Q1 equal to 1 minus T2 by T1. Okay, so now if you do some calculation, you will be getting Q2 by Q2 irreversible by Q1 irreversible minus Q2 by Q1 would be uh, less than 0. Now we already know that Q2 by Q1 is already T2 by T1, right? So from here you can write also Q2 irreversible by T2 is plus Q2 irreversible Q1 is reversible by T1. So we are just basically taking the opposite of the sign. So Q1 is reversible by T1 plus Q2 is reversible by T2 less than 0. Okay. So that means during this whole process, this whole irreversible process from moving 1 to 2 and 2 to 1, during this irreversible process, this Qi by Ti is less than 0. Okay. Now we can write this thing in the differential form also. Okay. In the differential form, if you write it, it looks like this. So during this relation is this for this sign is basically denotes closed integral. Okay, so closed integral, see, it's a cyclic process. This if you convert this summation into integration, so the summation will convert to integration, right? So since it's a cyclic process, so instead of using just a normal integral sign, we use the closed integration sign. So dq by t will be less than 0. Okay. So this is basically known as the Clausius inequality. Okay. So there is also less than equal. So this equal to signs comes for case of the reversible one. Okay. So if you consider any kind of process, it can be reversible or it can be irreversible. So in that case, this inequality always hold. Okay. So this is known as Clausius inequality. Okay. So this holds for both the case of reversible and as well as the irreversible process. For irreversible process, the dq dt integration, closed integration during the cyclic process would be smaller than 0, and the closed integration will be equal to 0 for the case of reversible process. Okay. Now the next thing is, so is this from this concept of this inequality, there's we can also derive the concept of entropy also. Okay. If you see the concept of entropy, okay. So let's suppose there is a process is going on from all of this 1A to B, 1 some 1 to 2. So there are multiple paths it can take uh, from there's a let's suppose that this is a reversible process. Okay. So it can take, so from state 1 to state 2, it can take this path, it can take this path, it can take this path, any kind of path it can take, right? 1A, this is let's say B, and this is let's say C. So let's take first take the case where the system goes like this and comes back like this. Okay, 1A 2 and 2B 1. So in that case, the path would be 1A 2B. Okay. So system goes like this, come back like this. Okay. This is a cyclic process. This is a reversible cyclic process. In that case, the dq by t will be equal to 0. Since it's for a reversible case, we know it's equal to 0. So this gives us basically 1 to 2 from path A, dq by t plus 2 to 1. So it comes back from 2 to 1 from path B, dq by t equal to 0. So basically we divide this closed integral into two different integral, from 1 to 2 and from 2 to 1. Okay. Now, so the similar way we can also write, let's take another process from 1B2 to 1 1B2 to 2C. So it comes from 1 to 2 and 2 to 1 using this B2. It goes back during this using this path B and comes back using this path C. Okay. So in this way also, if you do the integration, it will take some kind of this kind of form. Okay. So in this way, if you take the different path, and whatever path you can, you will, if you do that for any kind of path, whatever path you will take from 1 to 2 using a reversible way, you will see this this quantity dq by t will remain constant. Okay, whatever path you took from 1 to 2, whether it is a or b or c. So whatever path you took, you will see that this dq by t from state 1 to state 2 will always gives the same value. Okay, so it takes a constant value. Okay, so that means there is some kind of a state function exists, or state property of the system exists, which state property, that means you already know that it's only depend upon the initial and final state of the system. Okay, it doesn't depend whatever the path you took from reaching the initial, from reaching initial to final. Okay, it only depends upon the state. Okay, so that state function we are denoting as the entropy. Okay, so this entropy is delta S, we're denoting is delta is nothing but dq by t. Okay, so 1 to 2 is delta S, that is S2 minus S1. So this entropy is this S2 minus S1. So it is a state property. So this entropy, this is entropy denoting is a state function. Okay, this does not depend whatever path you took, A, whether it can take path A and comes back to B, or you take path B comes back at C, or you take A and comes back at C. Whatever you took, the delta S should be same for the for whole for all of the cases. Okay, and that so that quantity you are telling it as entropy. Okay, now there is also a relation process inequality relation also exists for the case of entropy also. Okay, so for the case of reversible process, this entropy final minus entropy initial will be equal to dq by t integration initial to final. And for the case of, this is for reversible process, and for irreversible process the initial and final is related, so it would be greater than, sorry, it would be greater than dq by t. Okay, initial final. Okay, this is for irreversible process. Okay, now you can calculate this entropy change for different types of processes. Okay, so let's consider a process. Okay, so these are very important actually, these relations of entropy. Uh, so let's take a process where there is a change of temperature. Okay, from, let's suppose T1 to T2. Okay, so I'm just writing it. So entropy change for delta T. Okay, so in this case, let's suppose that temperature of a system change from T1 to T2. Okay, so we know delta, what is the change of the entropy in that case? Okay, so you know delta is basically dq by t, and temperature is changing from, let's suppose, T1 to T2. Now we already know that dq is nothing but, so if there is change in temperature, so the heat change that is associated with the temperature change, we know is related by mc dt, right? So C is basically specific heat of that particular substance. Now if we substitute here, so T1 by T2 for the mc dt by T, so delta S will become MC. So dt by t, if you integrate, it will become log r, natural log. So it become ln t2 by t1, right? That is the delta S. Now let's suppose it's an isothermal process. Okay. So entropy change for isothermal process. Okay. For isothermal process, we know that dt is equal to 0, right, for isothermal process. So dq, is du plus dw, right? Yeah. Now, so since the dt is 0, so du is also equal to 0. So dq in this case would be dw, that is pdv, right? Now, so now in this case, the change in entropy would be delta S P dV by T, right? Now, if it's ideal gas, we know dV equal to nRT. So P by T would be nR by V, right? So nR by V, if you substitute it here, it will become delta S will be equal to uh, nR dV by V. If you integrate from V1 to V2, let's consider the change in volume from V1 to V2. It would become nR V2 by V1. Okay. So for isothermal system, the change in entropy is related by this formula, given that the volume is present, the volume is mentioned into the problem. Okay, so these are the different. Also, like for the case of phase transition, also you can calculate this change in entropy. So for the case of phase transition, also that is related with the latent heat, because phase change, the dq will become dq is simply will be equal to the latent heat exchange. Okay, so dq will become ml. Okay, so delta S would be in this case become ml by t. Okay. During the phase transition, the system remains at a constant temperature, right? So the latent heat is exchanged, so that expression is ml. So delta S will become ml by t. Okay. These are the the entropy change for different types of, like, some of the different types of processes we have discussed. So these are very important actually. So depending upon the problem, whatever the process you mentioned, you have to we have to use either of these formulas. Okay. Next, will we discuss some problems? Okay. So the problem one, uh, steam turbine is operated with an intake temperature of 400 degrees centigrade and an exhaust temperature of uh, 150 degrees centigrade. What is the maximum efficiency achieved for a given heat input? Okay. So option A is 0.41, option B is 0.63, option C is 0.37, and option D is 0.17. Okay. So we have discussed that from Clausius theory that sorry from Carnot's theory is that no engine is the efficiency of no engine can be higher than a Carnot engine, right? If the heat engine is operated between a particular to temperature, okay. So in that case, the Carnot engine efficiency would be the maximum one, okay. So for we know for Carnot engine, the efficiency is relation of the efficiency if it's working between two fixed temperature. The expression of the efficiency is given by T equal to 1 minus T2 by T1, right? Uh, and so we have to calculate uh, what is the maximum given heat temperature. Yeah, yeah. So so 1 minus T2 is here. What is the T2? T2 is here. So T2 is mentioned as the T2 is where the heat output is heat output is moving. So that is at exhaust temperature, right? So exhaust temperature T2 is as 150 degrees centigrade. So this thing have to convert it into Kelvin. This is a very important state. You cannot use any unit in degree centigrade into this on these formulas actually. So you have to convert it into the Kelvin. So this would become 423 Kelvin. Okay. Similarly, T1 is here. That is the hot reservoir. So that is at 400 degrees centigrade, right? So in Kelvin, it would become 673 Kelvin. So it would become 423 minus 673. To calculate this, it would give you 0.37. Okay, so this is the right answer. Okay. Next is 5 kg of water at 0 degree centigrade is mixed with equal mass of water at 80 degrees centigrade. Calculate the change in entropy. Specific heat is mentioned for water is 4.2 kilojoule per kg per Kelvin. Okay, uh, so the options are option A 69.3, option B 345.8, option C 1286.1, and option D 237.9. All are joule per Kelvin. Okay. So first, what happens that the water at 0 degree centigrade is mixed with the water at 80 degree centigrade. Now, in that case, what would be the temperature of the mixed water? Okay, like the final temperature of the mixed water. That we know we know the relation, right? So one so mCdt would be initially it's so from 40 degree. So from 0 degree, sorry. So the 0 degree part of the water will increase its temperature, right? So T final minus 0 degree equal to MC 80 degree minus T final, right? So from here, the T final would be half into 0 plus 80, so that would be 40, right? So 40 degree centigrade would be the or if in Kelvin, it should be 313 Kelvin is the temperature of the final mixed water, right? Now, so that means so there are two things. So there are two process that are involved, which basically results into the change in entropy. First is that some part of the water temperature got increased from 0 degree centigrade to 40 degree centigrade, and some part of the water its temperature got decreased, right, from 80 degree centigrade to 40 degree centigrade, right? So during because of these two processes separately contribute to the change in the entropy. Okay, so for this process the delta is 1 is simply uh, we know that for this is changing the temperature, right? We have already derived what is the formula of change in entropy if you change the temperature. So the change in entropy delta is 1 would be simply mc into ln t final by t initial, and for delta is 2 it would be mc ln, it would be also t final by t initial. Okay, now so delta is would be delta is 1 plus delta is 2, so that would mc ln, so it would first term would be t final is 40 plus, sorry, 313 by 273 plus mc ln 313 minus by initial is 353, right? That is 80 degree. So if you calculate this, it would give you. So C you already know. C is this thing. This specific heat 4.2 kilojoule. Okay. So since it's kilojoules, we have to convert it into the joule. Okay, 4200 joule per kg. Okay. And the mass of the water is also given as kg. So m is also 5 kg is given. If you substitute all of this thing here, you will be getting deltas as 345.8 joule per Kelvin. Okay, so this will be the correct answer. Now the 3 gram of nitrogen doubles in volume at constant temperature. Calculate the change in entropy. Okay, given the molecular weight of nitrogen is 28. So the options are option A 0.862 joule per Kelvin, option B all are in joule per Kelvin 0.523, option C 1.217, and option D is 0.617. Okay. Now the answer is, so yeah, so here, so the volume is changing. So temperature remain fixed, and the volume is changing for this process. So uh, since we know that for the volume change in volume, we know we have already derived what is the change in entropy. This is the formula, right? This formula I have already derived. So we'll use this formula. So nr ln v2 by v1 So just I'll just use this formula. So delta S is nr ln V2 by V1. So the volume doubles, so V2 equal to 2 into V1. N is 3 grams of nitrogen, so molecular weight is 28. So the number of moles is basically 3 by 28. So 3 by 28, R we know is the gas constant, so 8.314 into ln 2, right? This is the delta S. So if you calculate this thing, delta will give you 0.617 joule per Kelvin. Okay. So the correct answer is option D. Question 4 is which law of thermodynamics suggests that there is a tendency for equalization of temperature? So the options are the zeroth law, the first law, the second law, and D is the third law. Okay, we know that from zeroth law, we know that concept of temperature, and we know that if two systems are in thermal equilibrium, so in that case, the temperature should be equal to each other, right? So this equilibrium, so this equalization of temperature basically comes from the zeroth law of thermodynamics. We already knew that, right? From the last class, I guess, discussion, we have discussed this statement of zeroth law of thermodynamics, right? So the correct option is option A, zeroth law. Now, question 5. Calculate the increase in entropy when 1 kg of ice at minus 10 degrees centigrade is converted into steam at 100 degrees centigrade. Given specific heat of ice equal to 0.5 kilocalorie per kg degree centigrade. So latent heat of ice, so specific heat of ice is given, latent heat is given. Latent heat of ice is 3.4 into 10 to the power 5 joule per kg. Latent heat of steam is also given, that is at 22.68 into 10 to the power 5 joule per kg, and specific heat of water equal to 1 kilocalorie per kg degree centigrade. Okay. Okay, so basically what is happening here? So there is a ice. So ice is at minus 10 degrees centigrade. Okay. So this ice is becomes steam, steam, steam at 100 degree. centigrade. This is ice at minus 10 degree centigrade, and the ice is 1 kg. Okay. So during this process, there are numerous other processes are also involved, right? So first, what happens? So the ice will become from minus 10 degree to 0 degree, right? So ice at 0 degree centigrade. Now from 0 degree, it will do the phase transition from 0 degree ice to 0 degree water, right? Water at 0 degree centigrade. Now from this 0 degree water will become uh, water at 100 degrees centigrade. So you are keep increasing the heat to the system, and for that all of these processes are happening on. So first it converted ice will heat up from minus 10 degree to 0 degree. Then it will be a phase change from ice to water. That so that in that case it will remain at same temperature 0 degree. Then again it will it will convert from like 0 degree water to 100 degree water, and after that it will do a phase transition from water to steam. Okay, so there is, you can show 1 2 3 4. There are 4 processes involved, right? So all of these 4 processes basically will have some entropy output. Okay, so all of this process will basically give some entropy to the system. Okay, produce some entropy to the system. Okay, so this product entropy production you have to calculate. Okay, so delta is equal to delta is 1 plus delta is 2 plus delta is 3 plus delta is 4. Okay, so delta is would be mc ice. Ice is the specific heat of ice, that is also mentioned here. So the temperature would be T. So here, so it was at minus so it's minus 10 degree, right? It was at minus 10 degree. So from minus 10 degree it will become 0 degree. So T minus 10 to become T0, right? The next process, this is the phase transition process. So ML ice, okay, I T 0 degree centigrade, right? Delta is 2. This is due to the phase transition. Third process is the water is from 0 degree to 100 degree, it converting. So then in the third process it would be MC water, specific heat of water, ln T 100 by T 0. And the third one is the phase transition from water to steam. Okay, so this is also, so in that case you have to involve the latent heat here also. So ml, so we need the latent heat of the steam here. So yeah, so ml steam by T100, right? Now we have to just substitute the value. So mass is mentioned, that is 1 kg. So 1 into C ice, that is 4.2, right? Uh, no, it's given in kilocalorie. So you have to convert it in joule actually. These all things are given in kilocalorie. So you have to convert this kilocalorie into joule. So to convert it into joule, you have to multiply it 4.2, right? 4.2 into 0.5 into ln of 273 by 363 plus this ml. So 1 into L ice is also mentioned, the latent of ice, that is 3.4 into the power 5. So 10 to the power 5 joule is given. So we are converting everything into kilojoule actually. Okay. Uh, you can see in the answer also, the all the options are given in kilojoule actually. So I forgot to write the options. So options are basically, let me write it here. Option A is 10.5752. Option B is 6.652. Option C is 8.714. Option D is 2.07. So all of them are given in kilojoule actually, kilojoule per Kelvin. Okay. So L ice, so that indeed of ice have to also write in kilojoule. So that is 3.4 into 10 to the power 2 by 373. Sorry, 273 plus mc. So m is 1 and 1. So the specific heat of water is 1 kilocalorie. So 1 into 4.2, that will give you kilojoule in terms of kilojoule into a ln of 373 by 273. And lastly, the specific heat of ice, sorry, specific heat of steam, that is 1 into 22.68 into 10 to the power 2 by 373, right? So you have to be careful about the units. Okay, so you have to convert the kilocalories into joule or kilojoule, whatever according to the problem. So now if you calculate all of this thing, you'll be getting the delta is as 8.714 kilojoule per Kelvin. Okay, yeah. So this would be the correct answer, option C. Now the problem 6. A reversible engine absorbs 1 into 10 to the power 5 joule of heat from source at 400 Kelvin, okay, and rejects heat to sink at 200 Kelvin, okay. Calculate work done by the engine, okay. So the options are option A 25 kilojoule, option B 40 kilojoule, option C 50 kilojoule, and option D 100 kilojoule, okay. So since it's a reversible engine, so it's a heat engine, so you can consider this engine as an ideal, as a Carnot engine. Okay, you can use the formula of the Carnot engine here. So eta is, so for a Carnot engine, you know eta is equal to 1 minus T2 by T1. Okay, and the general formula we know is W by U1. That is the heat input, right? Now, so the W, that is the work done, that we actually have to calculate is 1 minus T2 by T1 into Q1. Okay. So just so we got the formula. Okay. So you can see in this expression everything is mentioned into the problem. So 1 minus T2 is there. So T2 is a source, that is 400. Sorry, T2 is a sink, that is 200, and T1 is a source, 400 into Q1, that is 1 into 10 to the power 5 joule. So if you calculate it, it will give you 1 minus 0.5, so it's 0.5 into 10 to the power 5 joule. The answers are given in kilojoule, right? Yeah. So it would become 5 into 10 to the power 4 joule, so it would become 50 kilojoule, right? So 50 kilojoule is the right answer. Okay. So this is the problem 6. The problem 7. Okay. So the next problem is problem 7. When the temperature outside cold storage is 20 degrees centigrade, 2 kg ice melts per hour. What should be the hour of motor to run the refrigerator to stop melting of ice? Well, ice is given, the latent heat of ice is given 336 kilojoule per kg. Okay. So the options are given. Option A, 21.3 watt. Option B, 13.6 watt. Option C, 22.5 watt. And option D, 31.4 watt. Okay. So now, so how the refrigerator is working here is basically, so this is the refrigerator. Okay. So uh, in order to keep this ice uh, remain as ice, so what it has to do, it has to basically pull out that specific heat from this ice to the outside temperature, that is at 20 degrees centigrade. Okay. So now in order to pull out that particular ice, like particular specific heat, uh, so it has to do some work, external work from outside, right? This is basically the concept of refrigerator, right? This is the ice at 0 degree centigrade, right? It's in, yeah, it's 0 degree centigrade. Yeah. So this is T2. So in this case, this is the T2 that is at 273, and T1 is at 293 Kelvin. So what is the work done here? So per hour, okay. So our problem we have to we'll have to calculate in terms of watt. Okay, so we have to consider the units per unit hour or per unit second. What is happening? We have to calculate that also. Okay, so that we'll do later. So first, let's calculate the work done. So work done is is for an ideal case, we know Q1 by Q2, 1 minus Q1 by Q2 is equal to 1 minus T2 by T1, right? sorry, this is no, sorry, this is for the refrigerator. If refrigerator, the formula was given by this. Where is this? This one. So Q2 by Q1 minus Q2 equal to T2 by T1 minus T2, right? This is the coefficient of performance. So from here you can write like this: Q1 by Q2 is nothing but T1 by T2. Okay. So now here, so Q2 is the heat that is required, right? So uh, Q2 is the heat that you need to pull out from the ice to make sure that it doesn't melt. So that heat should be equal to the specific heat. So per hour, that specific heat Q2 is ml. So 2 gram of ice is melting per hour, right? So Q2 M is 2 and L is 336. Okay. So Q2 is 336. So Q1 equal to T1 by T2 into Q2. T1 by T2 is 390, sorry, 27293 by 273 into Q2. That is 2 into 336. That is in kilojoule actually. So that is, you have to convert in joules of 672 into 10 to the power 3 joule. Okay. So Q1 is basically, if you calculate it, it will give you 4.923 into 10 to the power 4 joule. So we got this, the joule. So this, so in 1 hour actually, this Q1, that is 4.923 into 10 to the power 4 joule heat you have to pull out. Now if you calculate it, you have, like in the answer and the options, you have to calculate this thing in terms of the power. Okay, so power means what is the joule per second, right? So you have to calculate 1 second how much joule you have to pull out. Okay, like you have to do the work. Okay, uh, just a second. So this is actually Q1 I've calculated. So okay, so we have to do the work done. So work done is W is Q1 minus Q2. Okay, so this thing I have to calculate, this W. That is nothing but Q1 minus Q2. So Q1 minus Q2, if you calculate, sorry, this is a different thing. So if you calculate Q1 minus Q2, so now if you Q1 by T2 by Q2 minus Q2, T1 by T2 minus 1 into Q2. Okay, so 293 by 273 minus 1 into Q2. So W will become, now here, if you do this calculation, you'll get this actually. 4923 into 10 to the power 4 joule. Okay. So this is the work done. Okay. So work done is nothing but Q1 minus Q2. That is the heat from here minus the heat here. Okay. Q2, Q1. So Q2, Q1. Yeah. Now this work done, you have to convert it into watt. So 1 hour is 4.2923 joule. 1 second is this thing 923 into 10 to the power 4. You have to multiply it 3600 second, right? To do that, it will give you around 13.6 watt. Okay, that is joule per second. So this would be the correct answer. Okay. Next problem is problem number 8. A Carnot engine with efficiency eta, so eta is 0.6, drives a Carnot refrigerator. So both are ideal. Okay. Refrigerator with COP, that is a coefficient of performance, that is equal to 5. Okay. Determine the engine absorbed from, determine the energy. Okay. Determine the energy absorbed from cold body by the refrigerator for each kilojoule of energy absorbed from the source by the Carnot engine. Okay. So the diagram looks like this kind of. So there are two engines. Okay, one is the heat engine. So it is doing work like this. It absorbs heat Q1. The engine does some work W. It rejects it to the colder body Q2, and this work done is take it as a work input into the refrigerator. Okay, so this refrigerator is working between uh, T3 and T4. So here this is the cold, this is the hot. Here this is the cold, this is the hot. So here heat is flowing on the opposite direction. So this is like this. This is the heat engine here. Here it is the refrigerator. Okay. So whatever heat that is, whatever work done that is pulling out from this heat engine is used in the refrigerator. Okay, which helps the heat to pull out from cold to hot. Okay. Now for this case, what is the energy absorbed at the cold body? You have to calculate. Okay. So to do that, first thing you have to calculate what is W. That is uh, used as a work input into the refrigerator. Okay. So let me take the options also. The options are A. Okay, let me do it here. Okay. The options are option A 3 kilojoule, option B 5.36, option C 8.61, option D 1.25. Okay. So first what you have to do, what is the work done? Okay, from the heat engine. So that the same work done will be there also in the refrigerator. So eta we know is W by Q1. Okay, so W would be eta into Q1. So here Q1 is for each kilojoule it's mentioned. So Q1 is 1 kilojoule, right? 1 kilojoule. In the problem it's mentioned for each kilojoule. So Q1 is 1 kilojoule. So W will be eta is 6, so it would be eta is 0.6, so it would be 0.6 kilojoule. Okay. So you got W. Now this same W is used also in the refrigerator. So for the refrigerator, this coefficient of performance, that is COP, is defined as Q cold. That is, this is the Q cold. Q cold by W. Okay. So Q cold, that Q cold actually have to calculate. Okay. So the energy absorbed from the source. To calculate energy absorbed from the cold body. Okay, that you have to calculate. So Q cold is basically COP, that is 5, equal to work done, that is 0.6 kilojoule. So this would become 3 kilojoule, right? So the correct action will be 3 kilojoule. Okay. Okay, so this is our last problem. So if anyone have any doubt, you can ask. If you have no doubt, then I will just end the class here.